Hey everybody, this is our video for 4.1 through 4.6 out of the physics text. And we're going to talk about a couple different concepts that hopefully you have some background with and that you're aware of how they impact the world and how you've seen them in the world around you. The first thing that we're going to need to talk about to help us understand things that we're going to calculate and what we're going to try to understand is the concept of a force. Okay? First, we need to understand that a force is a push or pull on an object. Okay? So if you think about anytime you've been pushed, pulled, even when you lean against something, it doesn't have to physically move for it to be a force being applied to it. So just think about all those pushes and pulls that happen in the world. Everything from gravity pushing and pulling us downward to when you jump and you leave the ground, that's a push against the ground. The wind blowing through your hair is pushing against your hair. And so those are all things that we experience as force. A couple things we need to understand. Force, it is a vector, okay, which means it has direction as well as magnitude. And so it adds similar to other vectors. Okay. Other thing you need to know is that when we measure force in sort of the Americanized units, we'd be talking about pounds of force. Here we're going to be talking about what's called a Newton. Okay, a Newton of force. We use a capital N for its unit, similar to a meter or a second. We use a Newton when we talk about force. The reason we call it a Newton and have that reference is because Newton did so much work with regards to forces and understanding the basic motion of objects. And so if we look at, he has three laws, Newton's three laws of motion. The first law is what we call the law of inertia, okay, which is to say that an object in motion will stay in straight line motion at the same velocity, or an object at rest will stay at rest unless it's acted upon by some force. In other words, things keep doing what they're doing, no matter what. The second law of motion that Newton gave us was that if an object does have an imbalance of force, there will be an acceleration proportional to that force and inversely proportional to its mass. What that really comes out to give us is that if you add up, this funny symbol stands for summation. If you add up all the force vectors, should be a better arrow. It's a vector. If you add up all the force vectors, that will equal the mass of the object times the acceleration that it experiences. So again, acceleration and force are both vectors, and they will point in the same direction. Whatever direction the net force is, the total force, it will be the same direction that the acceleration is experienced. And the third law of motion, from Newton is the law of equal and opposite reaction. So if I think about applying, let's call that the wall, and I apply a force, we'll call that F1 on the wall is going to apply a force F2 against me. And the harder I push, the harder the wall pushes. So that F1 will equal F2. These two forces are going to balance each other out. Okay? So these are our three laws of motion. A couple other things you need to understand. When we talk about mass in this class, mass is going to be measured in kilograms. Okay? And newtons is obviously our force. The reason this matters, it actually has a lot to do with interpreting problems. When we talk about a problem, oftentimes we'll be given information about an object. We might be given the mass, we might be given the weight. Weight and mass are not the same thing. See, weight, when we talk about pounds of weight that we carry in the U.S., the equivalent to that, the analog, would be newtons, not kilograms. And so we have to understand this connection between these two. If you think about force as being mass times acceleration, if we let the acceleration be the acceleration due to gravity, okay, meaning gravity is what's pushing us down, then the force that we call our weight, okay, if you want to give it a name, would equal the mass that we have times gravity. This is something we're going to commonly use when we talk about the object's weight. mass times gravity. Notice it's not mass, it's mass multiplied by our value for gravity. So we have to understand when we see a newtons, if we talk about 58 newtons, that's something that has been either multiplied by gravity or by some other acceleration to create the newtons. If we see 58 kilograms, okay, that is a mass. And mass does not depend on gravity. Okay? And whereas a weight or a force does depend on some sort of acceleration. Okay? Now, in the real world, we do a lot of problems where we're talking about balancing these forces. So we need to have a couple of labels that we can understand as we talk about forces. For instance, the force of gravity, that's often considered our weight. Okay? And we'll call that mg. Notice it's not the acceleration from gravity, it's the force due to gravity. We also have things like Ft. This would be the tension in a rope. Now, tension is actually hard to calculate directly. Typically what we do is we calculate how much weight it's supporting, and that helps us understand how much tension there must be in the cable. Other forces we'll talk about, we'll sometimes do an Fa, which is just an applied force. Okay, so that would be like I'm pushing or pulling on something, not related to gravity typically or tension. Tension is technically an applied force, but we're going to talk about these as the forces that we can't label another way, where a person is imparting a force. Other things we'll need. Eventually we'll talk about the force of friction. Okay. We'll talk about that later on in our next section. But today there's one other force. It's Fn. And this is called the normal force. Now you maybe don't know this about the word normal, but it actually has a mathematical definition for the word normal. Normal means perpendicular to a surface. Okay, so when we talk about being perpendicular to a surface, what we mean is that if an object is sitting on the ground, right, we know that its weight, or gravity's force, mg, is applied downward. Well, based on Newton's second law, that means the object should be accelerating, unless there's a balancing force, some force that's equal in size but opposite direction, in order to counteract that and zero out or net zero the forces. To do that, we have to have some application, some rule of like what is the force and what's the rule behind it. Well, all surfaces, when their pressure is placed against them, will apply a pressure or a force backward, okay, in a perpendicular fashion. That's not going to be super important until we get to inclined planes. When we start talking about slopes, the fact that it's perpendicular to the surface really matters. But for now, we can simply say that the normal force opposes the weight of the object, and that these two things, by nature, are commonly considered to be equal in size. Again, we'll get to situations when they're not equal, but traditionally and initially in our early stuff, they are going to be equal. Really, most of what you're going to be working with today is this concept of F equals ma. And it's pretty straightforward to work with. You got a mass, an acceleration, and a force. And for the most part, it's just that simple. You get 2 out of the 3, you evaluate, and you move on. Remember, this is measured in newtons, this is measured in kilograms, and this is in meters per second squared. So those are your units. The catch, the little hiccup that you're going to run into, is oftentimes you're being asked to find the force, but you don't know the acceleration. You're going to be given some information with the mass. It'll tell you the size of the object, but the acceleration, if it's ever missing, okay, if you ever don't have it, you're going to have to approach it as a kinematic problem. In other words, you'll probably know the initial velocity, the velocity at the end, maybe the change in position, maybe the time. You'll know some of those things, and that is how you'll find the acceleration that you need. So we're going to tie a couple chapters, a couple concepts together. Kinematics and forces go really closely together because that acceleration component is so closely linked. Hopefully that's enough to kind of get you through there. If you've got the experience with the kinematic, that should help you. If you're struggling, you've got to reach out. You've got to communicate where you're struggling and let me help you. All right? Good luck, and we'll see you in class.